Hello lovers, in this video we're going to be going through the first unit for AQA GCSE Chemistry, that is atomic structure in the periodic table. We're going to take you through everything carefully, logically, so pause it and make notes as you're going along. Then if you want some extra help with your revision, if you look in the links in the description down below, you'll see over on the website there are set free questions, set free flashcards to help you revise, to help you remember all of these facts. Also over there you will find links to our predicted papers for this year and the ones from last year, and then walkthroughs of all of the papers that we've done as well. So showing you exactly what the examiner is looking for in the exam.
What is an atom? An atom is the smallest part of an element that can exist. Atoms of an element are represented by a chemical symbol, and these symbols will always start with a capital letter and consist of one or two letters. As you can see here, oxygen is just represented with a capital O, and helium is represented with a capital H followed by an E. Now we need to know how small an atom actually is. Atoms have a radius of about 0.1 nanometers, which is 1 times 10 to the minus 10 meters. And the radius of their nucleus is less than 1/10,000th of that of the atom. So it's about 1 times 10 to the minus 14 meters. We've already mentioned this word element. We need to know though, what is an element? What is its definition? So we need to know going into your exam that an element is a substance made up of only one type of atom. If we look at our periodic table, which we will be given in the exam, you can see that we've got over 100 different elements. All of these different letters or pairs of letters within the periodic table that you can see here is representing a different element. And each of those different elements will have their own unique set of properties. Now, if we link this back with what we said an atom was, the smallest part of an element that can exist, we can see that we can represent an element by showing a substance made of only that type of atom. So here, for instance, I've got an atom of carbon, and the element of carbon is just shown as lots and lots of these atoms in a structure. So now we're going to look at compounds. What is a compound? We should know that a compound is a substance which contains two or more different elements which are chemically combined in fixed proportions. So an example of this could be the chemical reaction that occurs between iron and oxygen to form iron oxide. Here we should recognise that iron and oxygen are both elements because they're only made up of one type of atom, whereas iron oxide is a compound. You can see it's made up of two different elements, the iron and the oxygen, which have become chemically combined. Now, it's important that we know that compounds actually have different properties from the elements that made them. So the properties of iron oxide are actually very different to the properties of iron and of oxygen. Now, we also need to know that compounds can only be separated into elements by chemical reactions. We aren't able to simply separate them using filtration or distillation or some other physical process. We have to use a chemical reaction. Now, chemical reactions will always involve the formation of one or more new substances, such as this example here, where iron and oxygen made iron oxide, and they will often involve an energy change. So quite often we'll observe an increase or a decrease in temperature due to this energy change. In chemistry, we're often going to be asked about chemical reactions. We might be asked to write down the word equation, which would look like something like this: water goes to hydrogen plus oxygen. However, sometimes we'll be asked to write down the symbol equation. Now this involves writing down the chemical names for each of these substances. So we know that water is H2O, hydrogen is H2, and oxygen is O2. Now, when we're asked to write down the symbol equation, we will need to balance it. And this is a certain skill. When we want to balance a symbol equation, we need to make sure that we have the same number of each type of atom on each side of the arrow. So on both the reactant side on the left and the product side on the right. Now let's use this as a perfect example to show you how to do this. The first thing I like to do is to separate the reactants from the products by drawing a little line. And then on the left-hand side, on the reactant side, let's count up how much of each type of atom we have. I can see I have 2 H's and 1 oxygen. Now if I do the same on the other side, I can see that I have 2 hydrogens and I have 2 oxygens as well. Now, looking at this, I can see I have the same number of H's on the left and the right. However, I only have 1 oxygen on the left and I have 2 on the right. Now, the way we can balance this is by having more waters on our reactant side. So let's write another H2O there. Now here I can clearly see that I have 2 oxygens. So I would cross out that 1 and replace it with a 2. However, by introducing another water, we now have more hydrogens as well. So we cross out the 2 and we replace it this time with 4 because I had 2 of these H2s. So now, although the oxygens are balanced, the hydrogens are now not balanced. So what we need to do is we need to have more hydrogens on the right-hand side. So let's introduce another H2. Now I can see H2 plus an H2 is going to give me 4 hydrogens. So now the hydrogens will also be balanced. I have 4 on the left and I have 4 on the right. So this means that our equation is balanced. Now let's write this in the way that the examiner would want it. I can see I have 1, 2 waters on my left-hand side. So I'm going to put a big number 2 in front of the H2O. That means that we have 2 waters. So now let's look over on the right-hand side. Here I can see that I have 1 and 2 hydrogens, which means I want to put a big number 2 in front of the H2. And there we have it, we have our balanced symbol equation. Now, in order to write down all of these balanced equations, there's some formula that we really need to know. And this is going to hold throughout the whole of chemistry. We need to know that carbon dioxide is CO2. We need to know that water is H2O. We need to know oxygen is O2. Hydrogen is H2. Nitrogen is N2. Ammonia is NH3. Hydrochloric acid is HCl, and sulfuric acid is H2SO4. If we learn these off by heart, we will have such an easier time in our exam. The atom is made up of 3 different types of particle. So we have protons, which are positively charged particles found within the central nucleus of the atom. Then we also have neutrons, which are also found inside the nucleus of the atom. Neutrons, however, have no charge. Now we might see this referred to as being neutral. Now that third particle found within an atom is the electron. Now electrons are negatively charged particles, and we don't find them in the nucleus this time. We find them in shells which orbit the nucleus. So you can see all this in our little diagram here. And we have to get very used to these diagrams and being able to label them accurately. This table here summarises all of the facts that we need to know about the protons, neutrons and electrons. We need to know that the relative charge of a proton is +1, the relative charge of a neutron is 0, and the relative charge of an electron is -1. We also need to know that the relative mass of both the protons and the neutrons, so both particles found within that nucleus, is equal to 1. However, the electron's relative mass is really tiny compared to this. We might see it referred to in several different ways, but essentially, the relative mass of an electron is approximately 1 over 2,000, or we may even sometimes see it referred to as just very small. Now, it's important that we know a few key facts relating to this information. So atoms of different elements will all have different numbers of protons. This is part of what gives them different properties. However, all atoms of a particular element actually have the same number of protons. Now finally, if we have a think about the mass of an atom, we can see that the relative mass of the protons and the neutrons is so much more than that of the electrons. And this is why almost all of the mass of an atom is found within the nucleus. In chemistry, we will often see isotopes coming up. Now we need to know what is an isotope. Isotopes are atoms of the same element that have the same number of protons but a different number of neutrons. Here you can see I've got two different isotopes of helium. The helium-4 isotope has 2 protons, 2 neutrons and 2 electrons. However, the helium-3 isotope has 2 protons, only 1 neutron and 2 electrons. So notice here, the thing that makes these isotopes of each other is that they still have the same number of protons, however they have a different number of neutrons. Now let's have a think about the ion. What is an ion? An ion is a charged particle which forms when an atom or a molecule gains or loses an electrons. So here I've got a diagram of a beryllium atom. I can see that it has 4 electrons. Now the beryllium atom can lose the 2 electrons within its outer shell to become a beryllium ion. Now because it's lost 2 of these negative electrons, it has become more positive. Think about it like if you lose a negative thought and you become more positive and happy. That's exactly what this beryllium has done. So because it's lost 2 electrons, it now has a 2+ charge. And this is how we would represent this in an exam. Electrons are found within shells. Now shells can also be referred to as energy levels, so use whichever one you prefer. When we're adding our electrons to an atom, we start by adding them to the innermost shell first. Now we need to know that in the first shell, that innermost shell, we can only add up to 2 electrons. Then in the second shell, we can only add up to 8 electrons. And the third shell, we only add up to 8 electrons again. Now this is going to be really, really important when we're in the exam if we're asked to add the electrons to an atom. So let's use carbon as an example here. Carbon has 6 electrons. Now if we want to add this to the shells, we can remember that we start with the innermost shell first. So with the innermost shell, we know that we can add up to 2 electrons. So we add our 2 electrons to the innermost shell of this carbon atom. Then if you think we have 6 electrons in total that we need to add on, if we do 6 minus that 2, we're left with 4 more electrons. And we know that in the second shell we can add up to 8 electrons. So we can fit all of those 4 in that second shell. And that's what I've done here. I've got 1, 2, 3, 4 electrons in its second shell. Now we can represent this using this diagram. However, we might also see it using this system here, where in brackets we do 2, 4. That represents 2 in the first shell and 4 in the second shell. Now let's have a look at how the atom is represented on the periodic table. Now the biggest number is known as the mass number. The mass number is very important because it represents the sum of the number of protons and the number of neutrons. Now the smallest number of the two is the atomic number. and the atomic number gives us the number of protons within that atom. So much information given just from this periodic table. So it's important that we know atoms have no overall charge. Now that then leads us on to the fact that in an atom, the number of protons, those positive particles, must be equal to the number of electrons, those negative particles. And that's how we can have no overall charge. Now we could be asked in the exam to work out the number of protons, neutrons and electrons in a certain atom. So if we look at fluorine here as an example, I know that that smallest number is the atomic number, which gives me the number of protons. Therefore, I know that the number of protons is equal to 9. Now then we can think about the mass number, which is the biggest number. And remember, we said that the mass number was the sum of the protons and the neutrons. So as we now know how many protons there are, we can work out the number of neutrons by doing 19 minus 9. And that ends up giving us 10. Now finally, we can work out the number of electrons by using the fact that we just said that in an atom, the number of protons is equal to the number of electrons. So using that fact then, we can say that we also have 9 electrons. And it's as simple as that. So let's carry out the same process now for an argon atom. I can see here that the mass number is 40, and I know that that mass number is equal to the sum of the protons and the neutrons. I can also see here 18, the smallest number of the two, is our atomic number. And I also, of course, remember that the atomic number is equal to the number of protons. So now that I've looked at this, I can start to work out how many protons, neutrons, and electrons we have. So because the number of protons is equal to the atomic number, I can say that I have 18 protons. Now, I know that the number of neutrons is going to be equal to that mass number minus the number of protons. Therefore, to work out the number of neutrons, I can do 40 minus 18, which gives me 22. So I know that I have 22 neutrons. Finally, to work out the number of electrons that we have, we use the fact that in an atom, the number of electrons is equal to the number of protons. So in this case, I can say that I also have 18 electrons. Sometimes we'll be asked a similar question, but to work out the number of protons, neutrons and electrons in an ion instead. So here we're asked for a Br- ion. We should understand that in an ion like this, which is negatively charged, we must have more negative particles than we have positive particles. Now remember that electrons are the negative particles and protons are the positive particles. So in order for bromine to have a negative charge in this case, we must have one more electron than proton. We can only have more or less electrons, not protons. That's an important fact. So if we look at this, we can see that that smallest number, the atomic number, is equal to 35. So using our knowledge from before, we know that the number of protons is equal to the atomic number. So we have 35 protons. Now we can see that the mass number here is 80. So to work out the number of neutrons, we use the fact that the mass number is the protons plus the neutrons. So to work out the neutrons, I'm just going to do 80 minus the number of protons, 35, which ends up giving me 45. So here I can see that I have 45 neutrons. Finally, we need to write down the number of electrons. And in order to do this, because we have an ion, we have to use the fact that we said that in this case, because it's Br-, we must have one more electron than the protons. So as we have 35 of these positive protons, we must have 36 of these negative electrons to get that overall negative charge. What is relative atomic mass? we need to know the definition of relative atomic mass is the average mass of all of the atoms of an element when compared to 1/12 of the mass of a carbon-12 atom. It's quite a technical definition, so definitely one to add to your flashcards. Now, the importance of relative atomic mass is that this definition explains why the relative atomic mass of some elements on the periodic table are not actually whole numbers. What they actually are averages of several different isotopes. Now, on the periodic table, we can look at chlorine and notice that its mass number is actually 35.5. Now, that is its relative atomic mass. That 0.5 has come about because we've averaged all of the different isotopes that exist for chlorine. It doesn't actually have 35.5 protons and neutrons. It's different to what we're used to. It's not quite the mass number in that case, it's just the relative atomic mass. Now remember, when we're talking about isotopes, they have the same number of protons, but a different number of neutrons. So all of those different isotopes of chlorine are still going to have 17 protons, however the number of neutrons that they have will vary. A very common type of question that we will see in the exam is being asked to calculate relative atomic mass. So here is the formula that we need to use. Relative atomic mass is equal to the percentage of isotope 1 multiplied by the mass of isotope 1 plus the percentage of isotope 2 times by the mass of isotope 2. And we repeat this process for as many isotopes as we have, adding them all together, and then divide through by 100, because all of these percentage abundances will of course total 100%. So the three steps we're using are 1, multiply the percentage abundance of each isotope by its mass, 2, add all of these together, and finally 3, divide by that total abundance. So if we're using percentages, that is of course going to be 100. Let's have a look at an example here. So lithium is found to have 2 isotopes. Lithium-6 has a 7% abundance and lithium-7 has a 93% abundance. Here we're asked to calculate the relative atomic mass of lithium. So first things first, let us remind ourselves of the equation. So we know relative atomic mass is equal to the percentage of isotope 1 times the mass of isotope 1 plus the percentage of isotope 2 times the mass of isotope 2. And then we add those together, divide by 100. So summarising the information we have here, we know the mass number of lithium-6 is 6 and its percentage abundance is 7%. Lithium-7 has a mass number of 7 and a percentage abundance of 93. So if we substitute these into our equation, we find that the relative atomic mass is equal to 6 times 7 plus 7 times 93 divided by 100. And that gives us a relative atomic mass equal to 6.93. And so that is the relative atomic mass of lithium. What is a mixture? We need to know that a mixture consists of 2 or more elements or compounds which are not chemically combined. So this diagram here shows what a mixture looks like. You can see we have a mixture here of these green molecules and these blue atoms. They are not chemically combined and therefore we have a mixture. So we need to know that mixtures can be separated by different physical processes. These include filtration, crystallization, simple distillation, fractional distillation and chromatography. And the method that we end up using of course depends on what makes up the mixture. Now these processes do not involve any chemical reactions and no new substances are made. So let's start by looking at filtration. Filtration is used to separate mixtures of insoluble solids, for example sand, and liquids such as water. As you can see from this diagram, we will pour a mixture of insoluble solid and liquid through some filter paper, which will be sitting in a funnel. The insoluble solid will end up staying in that filter paper because its particles are simply too large to pass through. And the liquid will pass through the filter paper and end up gathering inside our conical flask. Like we said, we would use this method whenever we want to separate a mixture of a solid, which is insoluble, and a liquid. Now let's look at simple distillation. Now, simple distillation is used to separate a solvent from a solution when we want to keep the liquid. So an example of this is we want to produce water from a salt solution. Let's have a look at this apparatus here. You can see that we have a condenser, which is an important piece of apparatus which cools down our gas vapours that will form to condense them back down to a liquid. So let's look at the method here. So the first thing we're going to do is we're going to heat up our solution. You can see we're doing that here using a Bunsen burner. So the liquid part of our mixture will evaporate, becoming a vapour and rising up. Now this vapour is going to pass through the condenser where it's going to get cooled down. But when it gets cooled, the vapour will condense back down to a liquid. This then separates the liquid from the dissolved solid, and we have successfully separated them. Fractional distillation is another method to separate substances. Now we use fractional distillation to separate two or more liquids which have different boiling points. Now this process is very similar to that of simple distillation, with one main difference to the apparatus, and that is the presence of a fractionating column. It's that fractionating column that is key to separating these two liquids. So let's run through the steps here. So the mixture is going to get heated to the temperature of the liquid with the lowest boiling point. Now the liquid with the lowest boiling point is going to evaporate first. It's going to rise up through the fractionating column and pass through the condenser, eventually cooling and condensing. Now when all of this substance has evaporated and condensed, we've separated the two liquids. Now let's have a look at crystallization. Now crystallization is used to separate a dissolved solid, a solute, for example sodium chloride salt, from a solution. So we do this when the thing that we want is that dissolved solid. So at the end of this process, we want to end up with that solid. Let's look through the steps. So the first thing we want to do is to gently heat the mixture in an evaporating basin. Now some of the solvent, for example water, will evaporate away, making the solution much more concentrated. Now we're going to remove this from the heat when the crystals begin to form. We're going to leave it to cool, and then we're going to filter it to remove any excess liquid that there may be. Finally, we're going to leave those crystals to dry. When they've dried, we have successfully separated our solid from the solution. Chromatography is used to separate mixtures of coloured compounds, for example inks or dyes. And this can be great for telling us if certain inks or dyes are made up of several different components or if they're in fact pure. So the way that we're going to do this is first we're going to start by putting a spot of the mixture along a pencil line near the bottom of a piece of chromatography paper. We place that paper vertically upright in a solvent, for example water. The solvent ends up getting soaked up the paper, carrying all these different components with it. Now different components are going to move at different rates, and this is what's going to separate them. Now if we had a pure substance, of course we wouldn't have a mixture. We'd only end up getting one spot on our chromatography paper. However, if we had a mixture, we would see the spot move up the chromatography paper and separate and give us two different spots, or more, depending on how many components there are to this mixture. Now, an important thing to know about chromatography, an extra little fact for you, is that we always use a pencil line. And they could ask you about why we do this. The reason for this is that pencil is insoluble in water and many other solvents too, and it doesn't move during the chromatography process. Imagine if it did, it would completely interfere with our results, so we always use pencil lines. Here we're going to have a look at the development of the model of the atom through time. So we started off with Dalton's model. Dalton's model told us that the atom was a solid sphere, cannot be created, destroyed, or divided into any smaller parts. Now, different types of spheres made up different elements. but this sphere did not contain any protons, neutrons, or electrons. Now, over time, J.J. Thomson came along and proposed a new model called the plum pudding model. Here he said that the atom is not actually a solid sphere. What it actually is a cloud of positive charge with negative electrons embedded within it. Next came along the nuclear model, and the experiment that determined this was Rutherford and his students' alpha scattering experiment. Now, what Rutherford and his students did was he fired alpha particles at a thin sheet of gold foil. Now, if the plum pudding model was true, we would expect all of these alpha particles just to bounce back. However, most of them passed straight through. Some of them were a little bit deflected, and very, very few came straight back. Now, what this told us was that the mass of an atom was actually concentrated in a central nucleus, which had to have been positively charged to have repelled this positive alpha particle. And most of the atom actually was empty space, completely contradicting the plum pudding model. And we know this because most of these atoms went straight through the gold foil with no deflection. So over time, Bohr came up with the electron shell model. And the electron shell model told us that rather than just randomly floating around the nucleus, the electrons were actually found in fixed distances from the nucleus, orbiting it in shells. Later experiments found that the positive charge of any nucleus can actually be subdivided into a whole number of smaller particles of equal charge. These were named protons. Finally, James Chadwick carried out some experiments that provided evidence to show the existence of neutrons in the nucleus. And this more or less brings us to our up-to-date understanding of the atom. Here we're going to have a look at a vital part of chemistry, the periodic table. We're going to use this so much throughout the course. So periodic table, why is it called a periodic table? It's because similar properties occur at regular intervals or periodically. Now let's have a look at this periodic table then. We should know that the columns are called groups and the periods are the rows. So we start with period 1, which is our first row. Then the next one is our period 2, period 3, 4, and so on. Now we need to know that all of the different groups have elements with similar properties within it. Now all of the elements within a group have the same number of electrons in their outer shell. This is such useful information. So for example, all of the elements in group 1 have just 1 electron in their outer shell. All of the elements in group 2 have 2 electrons in their outer shell, and so on. Another great fact to know is that elements in the same period all have the same number of electron shells. So hydrogen and helium in period 1 just have 1 shell, all of the ones in period 2 have 2 shells, and so on. Early periodic tables, like the ones here by Newlands, were incomplete, as many of the elements were unknown. Before the protons, neutrons, and electrons were discovered, scientists arranged elements in order of their atomic weights. However, this meant that some elements were placed into incorrect groups, as their chemical properties were ignored. Now, Mendeleev tried to solve this problem. He arranged elements in columns based on their similar properties. He arranged elements horizontally in order of atomic weight, but left gaps to allow for elements that may have been undiscovered up to that point. In some places, he changed the order of atomic weights to maintain the patterns in the columns. Now, over time, elements with the properties predicted by Mendeleev were discovered, filling the gaps. Now, isotopes explained why the order of atomic weight was sometimes incorrect. And that is how we got to the periodic table that we use today. Now, we need to know that elements that react to form positive ions are metals, and elements that react to form negative ions are non-metals. Now, on our periodic table, we need to know where we find our metals and where we find our non-metals. So let's have a look at it. If we look at this little staircase that we have here, where the staircase starts just above aluminium and goes all the way down, we can see that the metals are on the left-hand side of the periodic table and the non-metals are on the right-hand side of the periodic table. Let's look at group 0, or the noble gases. Now this is the column on the periodic table that is found furthest to the right-hand side. So the key facts we need to know about the group 0 elements are that they have a full outer shell of electrons, they are unreactive, and they do not form molecules. They are monatomic. They exist as neon or helium, not as molecules. So why are the group 0 elements unreactive? This is because they have full outer shell of electrons. So the next fact we need to know about the noble gases is how does the boiling point of the group 0 elements change down the group? We need to know that the boiling point increases down the group. The group 1 metals, or the alkali metals as they're sometimes referred to, have a few key properties. First one is that they all have one electron in their outer shell. And the second property we need to know is that they can react with oxygen, chlorine and water. Now we need to know, how does the reactivity of the group 1 elements change down the group? It's important we know that the reactivity increases down group 1. Why does the reactivity of group 1 metals increase down the group? Well, we need to know that the atoms increase in size as you go down the group. There are also more shells, and this means that the outer shell is further away from the nucleus. This means that the electrostatic attraction between the positive nucleus and the outer shell electron is weaker. Now this means it's easier to lose that one outer electron, making those elements at the bottom more reactive. Let's have a look at how the group 1 metals react with water. We need to know the general reaction is that metal plus water makes a metal hydroxide plus hydrogen. Now an example of this, of a group 1 metal reacting with water, is the reaction of sodium with water to make sodium hydroxide and hydrogen. The alkali metals get their name from the fact that when they react with water, they form this metal hydroxide, which forms an alkali solution with a pH greater than 7. It's good to know that heat is also given off in these reactions sometimes, and this can even sometimes be seen with a flame in these reactions. So what is observed when alkali metals react with water? Well, let's think about our equation, our general equation here. We're going to observe fizzing due to the formation of hydrogen gas, and we're also going to observe our solid metal disappearing over time, and this is because the metal gets used up. Now let's have a look at the reactions of those alkali metals with oxygen. We need to know that a group 1 metal reacts with oxygen to make a metal oxide. So an example of this is sodium plus oxygen makes sodium oxide. Now let's look at the reaction of group 1 metals with chlorine. So we need to know that a group 1 metal plus chlorine makes a metal chloride. And an example of this is sodium plus chlorine makes sodium chloride. The halogens are found in group 7 of the periodic table. Group 7 elements all have 7 electrons in their outer shell. They're all non-metals, and they all consist of molecules made of pairs of atoms. We call these diatomic molecules. So they exist as, for instance, F2, Cl2, Br2, etc. Now we need to know, how does the reactivity of the group 7 elements change down the group? We need to know that the reactivity decreases down group 7. So as well as knowing that the reactivity decreases down the group, we also need to know why. So we need to know the atoms increase in size as they go down the group. We need to know that there are more shells, and so the outer shell is further away from the nucleus. And therefore the electrostatic attraction between the nucleus and the outer shell is actually weaker. This means it's going to be harder to gain an electron to fill that outer shell, which in turn makes it less reactive. As we go down group 7, the melting and the boiling point of the halogens increases. Now this explains why the state changes from a gas to a liquid to a solid as we go down this group. But why does the melting and boiling point increase? We need to know these 3 points. The molecules increase in size, so the intermolecular forces become stronger, and therefore more energy is required to overcome the forces of attraction. And that is why the melting and boiling point increases. So here we have a table that summarises all of the properties about the group 7 elements that we need to know. So the state of room temperature goes from a gas to a liquid for bromine and a solid for iodine. We can see that as we go down the group, the relative molecular mass increases, as does the melting point and boiling point. However, the reactivity decreases down the group. We also need to know about the appearance of group 7 elements. We need to know that at room temperature, fluorine is a gas that is yellow in colour. We need to know that chlorine, at room temperature again, is a yellow-green gas. However, if we were to dissolve chlorine in water, it would appear a pale green solution. Bromine now, at room temperature, is a red-brown liquid. However, if we put that in water, it would appear orange. And finally, iodine is a grey solid at room temperature. However, in solution, it's actually dark brown in colour. When the group 7 elements react with metals, they produce salts. For instance, if we had sodium plus chlorine, we end up making the salt sodium chloride. The halogens can also react with non-metals such as hydrogen. Now, when halogens react with hydrogen, they form hydrogen halides. For example, if we had hydrogen plus chlorine, we end up making hydrogen chloride. So H2 plus Cl2 makes 2HCl. Hydrogen halides are gases at room temperature, and they dissolve in water to form acidic solutions. For example, hydrogen chloride would dissolve in water to form hydrochloric acid. Now let's look at displacement reactions for the group 7 elements. So we know that reactivity decreases down group 7. Now the more reactive group 7 elements can take the place of less reactive group 7 elements in a compound. This is called a displacement reaction. So if we have chlorine reacting with potassium bromide, we will see that the chlorine, which is more reactive, will displace the bromine, giving us potassium chloride and bromine. However, if we reacted chlorine with potassium fluoride, because chlorine is less reactive than fluorine, we actually have no reaction take place because the chlorine cannot displace the more reactive fluorine. This table here summarises the reactions and the observations that we need to know. So if we reacted potassium chloride with bromine or iodine, you can see that we get no reaction each time. That's because the chlorine is already more reactive than the bromine or the iodine, so no displacement takes place. However, when we react potassium bromide with chlorine, the chlorine will displace the bromide ions. Now, as a result, we'll end up forming potassium chloride and bromine. Now that bromine will be in solution, so we will observe an orange colour. Now, if we reacted potassium bromide with iodine, we would see no reaction take place again. And the reason for that is because bromine is more reactive than iodine. Finally here, if we have potassium iodide reacting with chlorine, because the chlorine is more reactive than the iodine, we get a displacement reaction take place. We end up forming potassium chloride and iodine. And because this is in solution, a brown colour is observed. Now the exact same thing happens with bromine reacting with potassium iodide. Again, the bromine will displace the less reactive iodide ions and iodine will be formed. And again, we will observe that brown colour of the iodine in solution. The transition metals are found in the middle of the periodic table, as you can see here. Now the transition elements that you may get asked about are chromium, manganese, iron, cobalt, nickel and copper. Now, it's important that we recognise that although transition metals and the group 1 metals are both metals, they actually have some very different properties. If we compare their melting points, their density, their strength and their hardness, we can see that these properties are all relatively high for the transition metals. However, they're relatively low for the group 1 metals. Likewise, the reactivity of the transition metals with oxygen, water and the halogens are very slow or maybe even not at all, whereas we know that the group 1 metals react very easily with these things. So what are the typical properties of transition elements? The first property we need to know is that they have ions with different charges. For example, we can get Fe2+ and Fe3+. They can also form coloured compounds. For example, iron 2 oxide forms a reddish-brown solid. And finally, they can be used as catalysts. For example, manganese 4 oxide increases the rate of decomposition of hydrogen peroxide. So there we have it. Those are the things we need to know about transition metals.
Ouch! This is why in some videos I have unexplained scratches.